In order to start learning about line integrals, the first step is to understand the concept of parametrized curves, okay? And this is a relatively simple concept, but it's fundamental that you understand it. So what is a parametrized curve? So a parametrized curve is a function r, which is a position vector, yeah, and this is a function of one parameter, which we typically call the parameter, we call it u, okay? So this vector r corresponds to some position vector x, y, z, such that x, y, and z are a function of u, okay? And that is it. This is a parametrized curve. You can interpret a parametrized curve as a black box, my usual depiction of functions as a black box, yeah, in which you input a parameter u and your output is a position vector r. Or you could imagine that you have actually three outputs, x, y, z, yeah? So x, y, and z. So how does this look like if we actually plot a parametrized curve? So for that I have a Mathematica applet. So here I'm showing a three-dimensional space. You can see the axis, x, y, and z, yeah? And then I'm plotting a curve in three-dimensional space, okay? This is a three-dimensional curve, fine? And here in blue, I'm plotting the r vector. This blue vector corresponds to this r here, okay? So this vector depends on the parameter u. And the parameter u, you can think of it as a slider, okay? And indeed, here in Mathematica, we have a slider corresponding to the parameter u. In this case, I called it t, but it doesn't matter. The name of the parameter is irrelevant, yeah? So when you change your value of the parameter, your blue arrow, which is the vector r, changes because r depends on the parameter, yeah? So as you move through the values of the parameter, you are moving through your curve. And typically, if you just specify a function r of u, you would be specifying an infinite curve. But typically, you also specify the limits. So you would say that u, let me move this, you would say that u goes between two limits, a and b. And by limiting the parameter u to be between a and b, you are basically like specifying what my minimum value of the slider is and my maximum value of the slider is, yeah? So here the parameter has different values. In this case, I'm going between 0 and 1. So this will specify a certain segment of your three-dimensional curve, okay? So now we have a segment of a curve. So that's basically the concept of a parametric curve. Let's look at some actual equations and the example, the curve that they represent. So consider this vector r of u, where we have x of u, which is a function, we have y of u, and we have z of u, which in this case is constant equal to 0, okay? So if you substitute different values of u in this equation, you are going to be always in the z equals 0 plane, because z is always equal to 0. So we are always in the z equals 0 plane, yeah? But of course, our x and y values are going to change when we change u. And you can recognize here the parametric equation of a circle. So actually, when we change u, we are going to move around the circle. And actually here, u is playing the role of the azimuthal angle, which we typically had called phi in the past. So phi would be our parameter, which now we are calling u, okay? So this represents a circle. Now this next example, this is interesting because it's almost identical to the past example, except that instead of having a constant r, which represents the radius of this circle, so now we have substituted r with u. So now the parameter u not only moves us along the angle because it appears inside the cosine and inside the sine, but it also changes the radius. Okay, so as we increase the angle, as we start at the x-axis, which corresponds to an angle of 0, now we start increasing the angle in this direction. As we increase the angle, the radius also increases. Yeah, so you can see that this forms like a spiral. And actually this spiral would continue to infinity, getting bigger and bigger. Okay? In here I have limited the values of u between 0 and 2 pi. That's why we only get one single turn around the z-axis. And finally, consider this example in which the x and y functions are the same as they were for the circle. Yeah, they are the same. But now the function for z, instead of being 0, now the function for z is equal to u, which means that as we move around the circle in the xy plane, when we increase the angle, we are also moving in the z direction. And that's why this now forms this nice spring or upgrowing spiral. Yeah. So the projection of this spiral is still the circle, but now clearly as we increase the parameter u, we are also moving upwards. So this creates this spring. So this is an example of a parametric curve. Let us do other examples of parametric curves. What if you want to parameterize a curve which you have written as y equals a function of x? So this means that you have your axis y and x, and let's say you have some function y equals f of x. Yeah. How do you parameterize this curve? To parameterize this curve, you need to find a vector r which depends on some parameter. Yeah, and this vector r will have an x and a y component. Here I'm assuming that we are in 2 dimensions only. So we need to find a vector r which points from the origin to a point in the curve, and that when we increase the parameter, we are moving through this curve. Okay. So one way we can do this is to say, okay, let's use x as a parameter. X will be our parameter. And therefore, our vector r, which will be a function of the parameter r of x, it must be equal to x as a function of the parameter, so x as a function of x, and y as a function of the parameter, which is y as a function of x. So x as a function of x is a bit silly. How do you write x as a function of x? Well, it's just itself. It's just x. And how do you write y as a function of x? Well, you write the equation f of x. Maybe this was a polynomial, right? So then you would write the polynomial here as a function of x. So in this way, we have parameterized this curve. Okay? So this will be the parameterized equation for this curve. And this is in 2 dimensions. That's why our parametric equation for the curve has only 2 dimensions, x and y. Okay? Next, what if we want to parameterize a straight line between 2 points? Okay, so let's go back to 3 dimensions, x, y, z. And let's say that I want to parameterize a curve that goes between point A and point B. Okay, I want to parameterize this straight line curve. How do I do that? So I clearly need to find an expression for the vector that points from the origin to any point on this line, and that will be my vector r, which depends on some parameter u. And I need to make sure that when I change this parameter u between the minimum and the maximum value, I go from A to B. Okay? And the way to do this is by thinking a little bit. So you could write r as a function of u, can be written as vector A, which would correspond to a vector. Let me draw it here. Let me first move r of u out of the way. So now I have space to draw what vector A is and what vector B is. So now r of u could be written as A plus u times B minus A. And why does this work? Well, it's very easy to see that if you substitute u equals 0, then you get A plus 0, so you get A. And if you substitute u equals 1, you get A plus 1 times B minus A. So the A cancels and you get B. Okay, so this means that by changing your parameter u between 0 and 1, you are changing between A and B. So now by changing the parameter u, you are moving the blue vector between A and B in a linear way. Okay, so this slider U now moves your vector from A to B. Okay, so I hope that made sense. And you will use it very often because many times the curve is just a straight line. So that was an introduction to parametric curves. And next we will see about how to calculate the tangent vector to a parametric curve. Thanks for watching and see you in the next video.